So we are required to carry out the stability analysis of an earthen embankment. In the stability analysis, we generally find out the factor of safety, which is given by the resting moment divided by the driving moment for a particular slope. We know that the slopes the slope of an earthen embankment will fail due to the sliding of a large soil mass along a curved surface. So this is a curved surface which is assumed to be the failure surface. So many of the investigators have established that the failure of the surface will be in the arc will be in the form of a arc of a circle. And this method of examining the stability of slopes of an earthen embankment is called Swedish slip circle method, or also known as the method of slice. Now for this method, if suppose we want to find out the stability of the downstream slope, so we select a point O, so and then draw a slip circle. Okay, so we draw a slip circle. So let OA be the radius R, and similarly OB is also the radius R. The angle between OA and OB is known as theta. So if you want to find the total length of the arc of a circle, it is given by R into theta. Now the portion between the slip circle, so this and the downstream slope is divided into number of slices of equal width. Usually the slices will be between around 8 to 12, and each of the slices will be of the equal width. Okay, the next step is to calculate the weight of each of the slices. So for example, select so for example, for slice 1 weight W1, W2, W3, W4, like W5, W6 and so on. So now the weight component is resolved into two components, that is a normal component as well as the tangential component. We find that the component n will pass through the center O and hence doesn't produce any moment. Similarly, for each of the slice, the component n will pass through the center O and hence doesn't produce any driving moment, but the driving moment is produced only due to T. So T is acting here at a distance r. So therefore T into r gives the driving moment, okay, which is responsible for the sliding. So like this, on each we find out T component and multiply by r, and if you go on adding each of the components like T into r will give the summation of T into r, which is nothing but the driving moment, which is MD. So now this sliding is resisted by the shear strength of the soil and also the frictional resistance. So what is frictional resistance? So we have studied in friction chapter that if N is the component, so then the frictional resistance will be the N times tan phi, and also the resistance is due to the shear strength, which is C into the arc length, so where C is the cohesion, unit cohesion of the soil. So I have explained all the steps here, so which can be how the which each of the steps, and how do you divide the slices and find out the weight of the component, how do you resolve into normal component and the tangential components, and then find them out. Similarly, we have, so where the shear strength is given by C into delta L. Delta L is each of the arc lengths and N times tan phi. So if you take this total component and multiply by R, so we'll get what is known as the restoring. So now for each slices we have to calculate. So therefore C is a constant. So therefore summation of all delta L, summation of all delta L will be nothing but the arc length. The arc length is given by, as I told in the previous slides, that is, it is R into theta, and summation of n, that is sigma n. So now we know Mr, we know Md, so therefore factor of safety can be calculated. So factor of safety is Mr divided by Md, which should be greater than 1.5. So there is a method to locate the center of, okay, the method is which is center O. which will be along this line. So how to locate this point O? So now for any given angle alpha, we have alpha 1 and alpha 2, which is given in the form of a table in different textbooks. For different values of alpha, we get alpha 1 and alpha 2. So then with this alpha with alpha 1 and alpha 2, we get a point P which intersects at point P. Now, if h is the height of the embankment, so we draw h here below the toe, and then at a distance of 4.5 times h, we get this point. From here, we pass on to point P. This we get this line. So now we select the point O on this line. So for a point O, for example, then we draw the slip circle, find out the factor of safety. Like this, for various points along this line, we have the different slip circles for which the factor of safety is calculated. The slip circle for which the factor of safety is least will give the correct slip circle which can be used for the designs. This is generally used for consultancies where the exact location of point O is not known, so that's why we do this trial and error. But for academic purpose, you can select one point O and then draw a slip circle and find out the factor of safety. Thank you.